Welcome back. In this section we will talk about the charging methods of EVs. We all know that there is a battery pack inside the EV and it needs to be charged from time to time. There are various ways to charge it. The three common ways are listed below. As introduced, conductive charging is the most common charging method right now, and it has two categories: AC and DC charge. The users have their flexibility to choose where to charge: at home, at workspace, or at public charging station. The inductive charging has already existed but still not standardized yet. The third method is battery swap. We will introduce them one by one in this lecture. One of the conductive charging methods is AC charging, which you may already familiar with. The advantages of this charger are that the battery can be recharged anywhere there is standard electrical outlet. It can easily communicate with the battery management system, BMS, thanks to the internal wiring network. This effect leads to higher performance and lower cost. On the other hand, this solution is suitable to the PHEV application, in which the specific energy is lower. However, the AC power has to be converted into DC power in the car, and there is a limitation of the power output. That is because the size and the weight restrictions of the onboard charger, and normally AC charge needs relatively long time. Another category of conductive charging method is DC charging. This solution is suitable for high power designs, and the power output of fast charges is limited only by the ability of the batteries to accept the charge. The charging time of fast charger is less than 1 hour. The benefits of DC charge are: it can be designed with either a high or low charging rate and is not limited in its weight and size. Off-board chargers are located outside the vehicle, and this setup provides more flexibility in terms of the power that can be delivered. Also, DC charge with high power requests less charging time. Nevertheless, DC charging requests higher investment of installation compared to AC charging, and you could access the DC charge port only at public charging stations. In order to have safe and reliable DC charging service, there are some challenges need to overcome. First is the adverse impact on power system, harmonic contamination, and high current demand superimposing on peak hours. Second is the availability of this method is restricted due to limitations with the supply network. Finally, since the off-board chargers and the BMS are physically separated, reliable communication is important to ensure correct charging conditions. Depending on the battery's type, voltage, temperature, and SOC supplied by a BMS, and the off-board charger should adopt a proper charging method. Inductive charge is the energy transfer from the power supply to the EV via magnetic induction coupling, based on the principle of electromagnetic induction at high frequency. A possible solution for the inductive charger is shown in this picture. The main idea behind inductive charging is the use of two electromagnetically linked coils. The primary coil is placed in the road surface in a pad-like construction linked to the electricity network. The secondary coil is placed on the vehicle, ideally on the bottom of the car, at safe distance from the passengers. The AC is rectified and converted to high-frequency AC power within the charger station. Then this high-frequency power is transferred to the EV side by induction. As we can see, the wireless charging is quite convenient, and it is less mess than the conductive charging, for it has no cable. For self-driving cars, wireless communication can take care of everything. No plug behavior needed. Moreover, inductive charge is safety-driven, that is suitable for all weather conditions. Of course, there are also many disadvantages like high investment, limited space and weight of charge pads, limited misalignment tolerance, inevitable induction loss, and the risk of exposure of individuals at radiation. There is another way to charge a car wirelessly. Dynamic charging, which is similar to static inductive charging. The energy transfer from the charger to the car is through magnetic induction coupling. In particular terms, coils connected to electric cables which used to provide the power are buried in the road. The coils emit an electromagnetic field that is picked up by vehicles driving over them and converted into electricity to charge the cars. There are quite a lot of advantages of dynamic inductive charging, for example, low standing charging time for customers, lower DOD, which leading to longer battery lifetime because the car can be charged regularly. Battery size can be smaller also because the battery can be charged regularly on the road. The main barriers of the dynamic inductive charging are related to the power transfer efficiency, the foreign objects on the road, the abrasion of the road surface, and the coil structure changes inside the road building materials may impact the features of the coils and reduce the power transfer efficiency. So far, the dynamic inductive charging is still in the experimental stage because there are many challenges to standardize it. The challenges are leakage field in and around the car. There should be a standardized limitation. Different ground clearances, car size, power level could lead to suboptimal operations. To choose an universal high-performance coil type for dynamic charging is a challenge. Real-time coil misalignment is hard to estimate for all different types of cars, but this is important for optimal control. Hence, we are still on the way to the commercial available dynamic inductive charging. The third method we are going to introduce is battery swap. The battery swap works on the basics of switching out the depleted battery and replacing the same with the full battery. The process involves driving out the battery switching bay. An automated process will position the vehicle, switch out the current battery and replace it with the full charged battery. The depleted batteries are charged in the station for later deployment. The benefits of battery swap is obvious, that there is no range anxiety, quickly and easy like refill your tank. This approach has seemingly quite some advantages over other charging technologies, but to get the market acceptance is the challenge. The main reasons are as follows. First, the requirement of standardized battery interface across multiple car manufacturers. Second, consumer acceptance of not owning the battery and having to change the vehicle battery. Third, to monetize the battery usage, there should be a foolproof way to estimate the battery's state of health to check for its usage pattern. The fourth challenge is from safety perspective. The electrical connection between the battery and the vehicle carries a very high current, and it is this connection that would need to be made or broken each time the battery is exchanged. At best, it will cause wear and degradation at the key link between the two components. At worst, it has the potential to cause a massive discharge, with all the consequences that may ensure. As a conclusion, there is still a long way to go to charge a battery more convenient, more efficient, stable, and economical.